right, welcome to another exciting edition of Physical Chemistry. This is topic number 3, second and third laws of thermodynamics. Overall, this is quite a bit easier than the first law, to be honest. It's a lot less complicated, let's put it that way. Right, that the first law was introducing a whole lot of stuff. This is much less. And honestly, a lot of we'll see later, a lot of this most complicated stuff I kind of cut out because it's not interesting to me. But let's get started. So first section is about entropy. All right, last topic we talked about the first law of thermodynamics. Energy cannot be either created or destroyed. All right, well, the second law of thermodynamics is going to state that all spontaneous changes are accompanied by an increase in universal entropy. Right? Universal entropy, that's the key word here. Right. Universal entropy. Right? That's not the same thing as the entropy of the system. Right? The entropy of the system can increase or it can decrease. It just depends on the particular reaction that's happening. But universally, it has to increase in any spontaneous change. All right. As it says, entropy is an important factor in every chemical reaction and phase change. So it's going to be involved in everything. Now, as it says, S of the universe needs to be positive for a change to be spontaneous. And like the first law, right, the total entropy of the universe is going to be the sum of the system and the surroundings. Right? Just like the total energy of the universe has got to be the total energy of the system and surroundings, right? Same difference, just with entropy. Now, every change is going to have some amount of entropy associated with it, right? Some changes will result in less entropy for the system, but will also add more entropy overall to the universe, right? For a spontaneous change, and it's still spontaneous, not for anything else, right? If it's not spontaneous, that means we're having to do work to make it happen. All right. So what is entropy? Now, the most common word associated with entropy is going to be disorder. Right? We usually talk about disorder, like disorder in the universe is increasing. Right? From a macro view, as I say, entropy is the tendency for energy to spread out as much as possible. Right? That's kind of the macro view. Right? Heat flow from a hot room to a cold room until both are the same temperature, until they've reached equilibrium, or I guess if they were suddenly isolated from each other. Right? We also see it in different phases of matter. Right? In this case down here, right, a solid has fairly low entropy. As you change it into a liquid, you increase the amount of entropy. And as you change that into a gas, you increase the amount of entropy even more. Right? Makes pretty good sense, right? But a clearer, more accurate word to think about entropy is the word possibilities, basically. So if a system has more possible states, it's going to have higher entropy. Right? And each possibility is termed a microstate. Now, in the book, they talk about they talk about the statistical definition of entropy, right? Where there's a Boltzmann formula for the entropy, right? We're not going to use that. I don't think there's even any questions about it, right? We're not really going to use that because figuring out the value of W, which is the number of microstates, is not necessarily trivial, right? It's going to be something like given to you. That's given to you. Everything else is kind of boring. But anyways, right? In this example here, right, we have 4 different colored little balls that can be distributed amongst these 2 lobes in, what is this? 12 different ways. 6, no, that's right. 6, 10, 16 different ways, right? So with just 4 different little balls here, right, and 2 lobes, we've managed to make 16 microstates, right? 16 possibilities. Now scale that up to a mole of atoms, right? You're talking about a million, billion atoms, basically, right? That's a lot of different microstates, right? Many different microstates. So it kind of adds up. Now, entropy can be affected by many things. Some of these, look at all of these, we'll basically be looking at throughout this chapter. All right. First one is going to be temperature. Right? And as the temperature increases, more energy is available to be distributed in more ways. Right? Right. Another way that the book talks about it is that the supply of energy's heat to the system results in molecules moving to higher energy states, so increasing the number of microstates and hence the entropy, right? But another way you can think about it is that this is the Boltzmann distribution of velocities, right? All of these are velocities. Try to highlight that. I think it won't let me write on mine. There you go. All of these are velocities, right? And as we increase the temperature from 100 to 1200 to 3000 Kelvin, right, we see the distribution becoming wider and wider and wider, right? We've increased the possibilities of the velocity, right? And we talked about this before, 1 or 2 chapters ago, right? That if we were at 0 Kelvin, we would expect everything to have the exact same velocity of 0, basically, right? Well, we go on from there. As we increase temperature, we increase the possibilities, and so we would expect to increase the entropy. All right, for volume, if we increase the volume of a gas, right, this is specifically of a gas, right? If we increase the volume of a solid or a liquid, that doesn't make much of a difference, right? Because their compressibility is so low, it's going to be a very small change in entropy. But for gases, right, when we increase the volume, now we have increased possibilities for these particle positions here, right? Increased possibilities for all these particles. They can be in many different places. It's the same thing going back as if we added a third lobe onto this example here. Now, you can get even more possibilities if you added a third lobe, right? Changes in phase are always definitely going to have big changes in entropy, right? Entropy increases as we go from solid to liquid to gas, right? And of course, when you think of entropy as disorder, quote unquote, liquids are definitely more disordered than solids, right? And gases are definitely more disordered than liquids, right? So thinking about it that way makes perfect sense, right? And mixing substances can cause an increase in entropy, right? If we think about these separately, right, as it says, new microstates to be available. If we think about it separately, if we just had these purple molecules and this side was empty, right? If we opened it up, we doubled the volume, we would expect that to be an increase in entropy, right? Just the same thing we did here, right? The only difference is that this left side happens to be already occupied by other gas molecules, right? But if they don't interact, if they're a perfect gas, you're doubling the volume and it's no big deal. If they do interact, then you're just getting like more interactions means more possible microstates even more, right? So it's kind of being, no matter what you do, you're increasing the number of possibilities, increasing the entropy. Now, unlike all enthalpy, which was H, but technically H had the definition. We said, come here. Well, I lost my pen. Here we go. We said last time that H was U times P plus V, or U plus PV. Sorry, that's the actual definition of H. But we never saw for H by itself, right? We always looked at delta H. Right? It was delta H, delta U, and then P delta V, right? Because H is constant pressure. All right. Well, entropy is going to be different, right? It can have an absolute zero value. So the absolute zero value would be 0. So this is the third law of thermodynamics, that theoretically, right, if you had a perfect crystal at 0 degrees Kelvin, right, you would have basically just one microstate, right? You would have, in these conditions, only one microstate, right? And that would be, in this case, 0 entropy, because everything would be reduced down to one microstate, unmoving, perfectly frozen in time, if you would call it that. Right. So there is some absolute entropy. We can do S, we can do delta S. We tend to do delta S a little bit more, but that's just because of, in chemistry, we're looking at changes more often than just the absolutes of a system. And of course, just like our delta H, right, we can have standard, we had standard molar enthalpy, right? We have the same thing, standard molar entropy, right? And we can base it off of the 0 number. At standard conditions, sodium solid has a standard molar entropy of 51.4 joules per Kelvin. And so this is going to be very similar to, we'll see that a lot of this is going to be very similar to what we did with enthalpy. Right? Very, very similar to that, just very slightly different. So entropy changes. The entropy change of the surroundings is not going to be equal and opposite as rho. This is opposite of enthalpy. Okay. So the entropy change of the surroundings is not going to be equal and opposite as a rule. Okay. Because if you think about it, if delta S of the universe can be a positive number for our spontaneous processes, right, then delta S the universe is S of the system plus S of the surroundings, right? If system and surroundings were always equal and opposite, then delta S of the universe would always be 0, right? It would always be 0. Not true, right? We know this is not true. Second law of thermodynamics says we can have positive or negative delta S of the universe, or it could be 0 too, but it's not going to be the same, right? But the surroundings in any system, right, is going to be basically a source or sink of heat, right? Especially if we define the system correctly. Right? You don't really calculate delta U for the surroundings, right? We don't really calculate delta H of the surroundings all too much either, right? We typically talk about changes in energy of the system, right? That's because, if a system does work on the surroundings, right? We're adding work. Well, the surroundings are assumed to be very, very big, so that any amount of work we do is going to be a very, very small change, really, basically, right? Very, very small change. Right? But with our heat, we can calculate that pretty easily. Right? So any of the heat that goes in and out of our system comes from or goes to the surroundings. Right? The change in entropy of the surroundings will depend on the amount of heat and the temperature of the surroundings initially. Right? So this is S of our surroundings equals negative Q of our system over T. Right? And of course, Q, if this is also at constant pressure, would be the same thing as delta H. Right? Same thing as delta H. All right, so this is our first basic definition of our, basic usable definition, let's put it that way, of all of our entropy, right? As the book would put it in its more technical variants, right? It's ds equals dq over t. Something like that, right? Which if you integrated it, with regards to Q, right? You'd get delta S equals Q over T, right? And then you do a lot of other stuff from that. All right, so on and so forth, right? But this is usually, these are good enough version of it. That's going to be very, very functional. Same difference, right? Same difference, really. Now, if we want to talk about proving that entropy is a state function, right? Because so many things rely on, so many of our properties that we're doing rely on S being a state function, right? If we talk about the standard molar entropy, right? That can only happen if it's a state function. Right? Well, one thing they talk about in the book is something called the Carnot cycle. All right, the Carnot cycle. So this is a 4-stage cycle. We're starting here. We're changing pressure and we're changing volume as heat is let in or let out, basically. So we start at a hot temperature. We start at a hot temperature, basically, right? It just says here, the Carnot cycle. Stage 1, the gas is in thermal contact with a hot reservoir, right? Thermal contact with the hot reservoir. And so we would expect heat to flow from the hot reservoir to the gas, right? So this is reversible isothermal expansion. Like, notice this is isothermal, right? That's the key thing here, right? And so we can calculate the entropy by simply doing Q over H, or sorry, Q over T. Right? You notice here that T is assumed to be constant, right? Otherwise, it would be delta T or something, other thing like that, right? It'd be more complicated. Right? T is going to be constant here, isothermal. Right? So all the heat that goes in is allowed to cause the gas to expand. Right? As it expands, the pressure decreases concurrently. Right? Now in stage 2, these are adiabatic. Right? Adiabatic, of course, means that heat does not flow in or out. Right? In this adiabatic expansion, now we are allowing the temperature to change. Right? We're allowing the temperature to change. And so our temperature goes from a hot temperature to some cold temperature. Right? Some cold temperature. Right? Hot temperature to some cold temperature. So in the first 2 steps, the only amount of entropy change is here. Right? Because when Q is equal to 0 in adiabatic expansion, then delta S is also going to be equal to 0. Right? So stage 2 doesn't have any entropy associated with it. Right? Now, if we go on to stage 3, right, contact is with the cold reservoir, right? Heat is going to be able to leave the system, right? Go into the cold reservoir, right? It's still isothermal, right? So the entropy change is going to be the heat that leaves, basically, over the temperature of that cold reservoir. Right? Same thing, right? Exact same thing as this, just instead of being in touch with the hot reservoir gaining heat, now it's in touch with the cold reservoir giving away heat. And then in stage 4, we still have this adiabatic expansion, right? Where the T, change this, rises from Tc to Th, right? Our temperature is allowed to increase, right? We're keeping the same amount of heat, right? When we increase the temperature, the pressure and volume are going to change. And eventually we're going to end up back where we were, ideally, right? That's what we have to prove a little bit. All right, but that's where we're going to start. So this is our Carnot cycle, right? When we add up all of the entropies, right, we only have 2 sources of entropy, right? QH over TH and QC over TC. Right, those are only 2 sources of entropy. So in this case, if we wanted to do the total delta S, right, it should be QH over TH plus QC over TC, right? It should be the sum of all the individual steps, right? And of course, this is assuming it's going to be a state function, which we'll show is going to be true. So doing a little bit of slight derivation, and we'll get to an actually useful number here. All right. Showing that entropy is a state function for a perfect gas. So if we remember back to last chapter, last topic, whatever you want to call it, all right, we said that Q is equal to nRT natural log of VF over VI, right? That was for expansion, right? That's for expansion. Isothermal expansion, right? Now, if we have two different stages, stage 1 and stage 3, where we're doing this isothermal expansion, right, then we would expect to have two different versions of this, right? But in this version, call this hot, right? It's going to be at a hot temperature. This version is going to be cold at the cold temperature for step 1 and step 3, respectively. Right. Now, for a reversible adiabatic process in stage 2 and stage 4, all right, temperature and volume are going to be related. All right, temperature and volume are going to be related. So if we go back, look real quick, we're going to call this, let's see, this is point A, this is point B, this is point C, and this is point D, just to help labeling ourselves. All right, so again, we can use these equations to talk about A to B and C to D, right? But we also need B to C and A to D. Right, B to C and A to D. So to relate those, right, from D to A, right, right. This is one of the versions we saw at the very end of the last topic. Right, adiabatic changes. We did a lot of derivation and stuff to get to this. Right, remember C in this case is CV. Little c in this case is CV molar over R. Right. Now don't worry, we're not really going to use this too much, so this is just bringing stuff back in, right? And then from B to C, going to be similar. V of C, I should say. V of B, C, H, right? Just relating, using that same equation that we had before, right? Just relating it between these two changes, right? Now, if we were to combine all of this together, like multiply these two together, right, and then cancel everything out, right? If you multiply all this together, cancel it all out, we would end up with VDD over VC equals VA over VB, right? Because the THs would end up canceling out, the TCs would end up canceling out, and then it'd be VA times VC equals VD times VB. Rearrange it to look something more like this. All right. Now, VA, VB, VD, and VC, right? These are all just different ways of saying final and initial volumes, right? We look at here, the final volume in stage 1 is VB, right? And the initial volume is VA, right? Initial volume is VA, right? All that other stuff. So for our QC, do like this, right? A QC, right? That's nRT natural log of, right, where's the ending port D, final volume is D, initial volume is C, right? VD over VC, right? And in the same way, instead of VD over VC, we can substitute this in, right? This equivalence here to be VA over VB, right? VA over VB, right? And then we can use the properties of logarithms to make something slightly different form. We put a negative here, and when we put the negative, that's like a negative exponent in our logarithm, right? We flip the fraction of our logarithm, right, by doing it to the -1 power, basically, right? My question would be, why would we want to do that, right? Why would we do that? Why would we want to put VB on top, right? Well, if you look at QH, now what's QH going to be? nRTH times the natural log of B over A, right? Stage 1 is VB over VA. VB over VA. Right. So when we put these together, like now we have natural log of VB over VA, right? Kind of, we put them all in the same form, right? Now if we want to find, right, the ratio, basically, if we wanted to put this over QC, right, what would we get, right? We'd have QH over QC equals nRTH times the natural log of VB over VA. On the bottom, we would have negative nRTC, natural log of VB over VA, right? And in doing so, right, N is going to cancel out, R is going to cancel out, natural log of V is going to cancel out. We'll be left with QH over QC equals negative TH over TC. Right. And then, so let's write that. QH over QC equals negative TH over TC. Okay. Right. And then if we rearrange it a little bit, like move TH over TC to the other side, rearrange it a little bit, right? What we'll see is that QH over TH plus QC over TC is going to be equal to 0, right? Now, this little form right here, not really useful, not super useful, right? It's still entropy, right? QH over TH is what we had for stage 1, right? That's literally what we had a long time ago, right? QH over TH is what we had, right? Stage 3 was QC over TC, right? We just gone a very long way to prove that when we add those two entropies up together, it should equal 0 for a perfect gas, right? For a perfect gas. Now, it's not a perfect gas, it's going to be more complicated, but we'll get there when we get there. Yep. Again, this not very useful. Like this thing is a lot more useful than this thing is, right? But that's all last chapter. This is the useful equation. Now, speaking of the Carnot cycle, one of the, what's the word? Not lessons. One of the results from it, right, is that any heat engine can be expected to have a certain efficiency, right? So this is eta, right? Greek letter eta. So squiggly in, right? So the efficiency of any heat engine is going to be the work, right? Work done divided by the heat absorbed from the hot source, or the QH. I mean, think about it basically, right? Whatever heat is absorbed, how much of it is converted to useful work, right? That's the efficiency. Ideally, we want it to be 100% efficient, right? Now, that would be basically impossible. That's impossible, right? Right, because if any spontaneous process, there's going to be entropy, increase in entropy. So some energy is going to be lost as entropy, but generally this is what's going to be, right? For the amount of energy we put in as heat, how much work is produced or converted into actual good work, right? Now our work can be expressed as the heat not reaching the cold source. And what does that mean? Right, so this is like the beginning 100% when you talk about that. And then at the cold source, we only get 50% reaching there. That means that the missing 50% had to be converted to work. That's all we're saying here, right? We're just writing work as a function of all of the heat that did not remain as heat. Basically, all the heat that changed into something else. Right? So the difference between hot and cold. Right? Do a little bit of rearrangement, right? QH over QH is 1 minus QC over QH. We get eta, the efficiency, being 1 minus QC over QH, right? And this right here is going to be our Carnot efficiency. Okay. Oh, sorry, not quite that. This right here is going to be the Carnot efficiency. There we go. Right? We just showed on this previous slide, right, that QH over QC equals negative TH over TC. Right. Well, we can start putting in all these other things. Right? We rearrange, we flip the thing so we get rid of the negative on TH over TC. Right? Substitute it in. Now our efficiency is 1 minus TC over TH. It's going to be much easier to measure, right? Measuring the temperature of something is fairly trivial, right? Fairly trivial. It's easy to know. And so it's very easy to use because now we're just going to have two numbers for temperature, and that's basically it. Right? But if we wanted to use this, since a certain power station operates with superheated steam at 300 degrees Celsius and discharges the heat waste in the environment at 20 degrees Celsius. And what's the theoretical efficiency? All right, so first thing obviously we need to do is that Celsius, not going to work, right? This is going to be 573.15, and this is going to be 293.15, right? Change it to Kelvin. All we want to be in Kelvin, right? Celsius is done. Right, where our efficiency, our Carnot efficiency, right, eta, I don't know if that's a good eta, but it's close enough, is 1 minus TC over TH, right? Go back. Yep, just want to make sure it's TC over TH. Right. Well, if we put these numbers in, 1 minus absolute value, this is the absolute value. Right, the absolute value of 293.15 divided by 573.15. Let's do that little bit of math. Calculator says 293.15 divided by 573.15 is 0.51. Right. And if you do that, our efficiency is going to be basically 0.49. or 49% efficient. And one thing you can do very easily to check yourself, if for some reason you don't remember that TC is supposed to be on top, right? If you do TH on top, you're not going to get 0.51. You're going to get, right? If you put TH on top instead of TC, you end up getting 1.95. Right? And if you do 1 minus 1.95, you're going to get a negative efficiency, which doesn't make any sense, right? That makes absolutely zero sense. So you always got to end up with a positive efficiency overall, right? If you don't get a positive number, that means you flipped TC and TH, which kind of makes it a little bit nice, to be honest. Right? A little bit nice. So let's move on to a short bit on entropy changes for specific processes. Right? Now, key definitions from this last section where we're still going to use, right? Basically the same thing, right? ds equals dq over t, right? Delta s equals q over t. Basically good. Now, when we talk about expansion, we've already seen this a little bit. We've already seen this a little bit. Right, so for a perfect gas, delta U is going to be 0. That's part of being a perfect gas. It's kind of annoying because it's the only thing that does it, but whatever. Right. So in isothermal expansion, we would expect W to be equal to Q, right? So if U equals Q plus W and U is 0, work and heat have to be the same, just opposite signs. Right. We saw previously in the first topic of last chapter, I believe, that work is equal to negative nRT natural log of VF over VI, right? Which means that our Q is going to be the same but opposite sign, right? nRT times natural log of VF over VI, right? We kind of snuck that in here, right, when we did all these things. We kind of snuck that in there. So our change in entropy is going to be, right, this is still Q over T, right? Q over T. Well, when we do that little bit of division here, right, T cancels out. And so our delta S is just going to be N times R times the natural log of VF over VI. Right, N times R times natural log of VF over VI. All right, if you wanted to, you could just remember Q being this and then do this very, very simple cancellation right there, right? One less equation to remember, but still going to be useful. So let's give it a whirl. All right, calculate the change in entropy of the gas when 15 grams of carbon dioxide is allowed to isothermally expand from 1 decimeter to 3 decimeters at 300 Kelvin. Okay. So we need delta S equals NR natural log VF over VI. Right. N is going to be easy enough, right? 15 grams, 12 grams in every 1 mole of carbon. That's going to equal 1.25 moles of carbon. Oh, sorry, my bad. This is not carbon, this is carbon dioxide. Carbon dioxide is 44 grams for every 1 mole. There we go. So 15 divided by 44 is 0.341 moles of CO2. There we go. Moles of CO2. All right. R in this case will be, in this case, we can just do R of 8.314. Right. We're going to have 0.341 moles. Right. In this case, our R can be 8.314 joules per mole Kelvin. Right. 8.314 joules per mole Kelvin. That sounds like a good number for R. Triple check. You know how tricky R is. Let's triple check R. Me. Where are you? Values of R. There you go. Yeah, 8.314 joules per mole Kelvin, right? And we can use this one, right? Because if we look at our natural log, right, whatever we put inside our natural log, final volume of 3 decimeters, initial volume of 1 decimeters, right? By sort of definition, our natural log has to be dimensionless, right? It has to be dimensionless. So really what we need to make sure is that the units inside of the natural log actually match. And they do, right? But when we divide these, we end up being dimensionless, right? Logs, natural logs can only ever be dimensionless, right? Which allows us to use whatever version of R we want, right? And we want the version of R, the simplest version, right? Where we get rid of moles and only have joules per Kelvin, which is the units of S. Well, if we do a little bit of calculation here, put this all together, and let's start with the natural log, not that log. I have to find my natural log now. Let me see. Okay. Oh, there you are. Natural log of 3, right, times 8.314 times 0.341 gets me 3.1111 joules per Kelvin. All right, 3.11 joules per Kelvin. Right. Not a huge amount, but that's okay. Right, it's very simple. Like it's a nice simple equation, right? We like simple equations. Now, we could do a phase transition, which is also going to be very, very common. All right, in a phase transition, right? Now we have for each phase transition a enthalpy of transition, right? We talked about this last chapter. Phase transition has a certain enthalpy change of delta H. Right? Delta H is Q at constant pressure, right? So, as it says, most of our enthalpies are given at normal transition temperature under 1 atmosphere pressure. And so, as long as this temperature is the same as the normal transition temperature, everything squares up basically, right? But for phase transition, super easy, just delta H over T, right? Super easy. An example here, enthalpy of chloroform is 29.4 kilojoules per mole, and its normal boiling point of 334.88 Kelvin. Calculate the entropy of vaporization at this temperature and the entropy change of the surroundings. Ouch. Ouch. Sorry. Popping my neck. So, we have right, delta H over T. Right, now one thing to note is this is, well, I guess the entropy of vaporization can go either way. So I was about to talk about the blue and the blue, the sign of delta S versus the delta H, but we're just talking about the entropy of vaporization, which is always given in positive numbers, right? It's always given in positive numbers, and depending on what direction you go, you apply a positive or a negative. Anyways, so going from there, right? Our delta H is going to be 2,000 or 29,400 joules per mole, right? We're going to change from kilojoules to joules because S, right? Enthalpy is pretty much always given in kilojoules. Entropy pretty much always given in joules. Right? And our temperature is 334.88 Kelvin. Right. So at this particular temperature, right, the delta S of our vaporization here is going to be 29400 divided by 334.88, which is 87.8. We'll call it 87.8 joules per mole Kelvin. All right, joules per mole Kelvin. Sorry about that. I had to go get a big drink of water. Talking too much, right? So this is our enthalpy of vaporization. Now, one key thing, which I don't think I mentioned so far, is that at our equilibrium, right, our total entropy has to be equal to 0, right? Because at equilibrium, nothing is changing, basically. All right, so our total entropy has to be 0, right? The system and the surroundings are in entropy. There has to be no net change, right? So given that being in mind, right, our 0 total entropy is going to be equal to our 87.8 kilojoules per mole, joules per mole Kelvin plus the entropy change of the surroundings, right? Well, the entropy change of the surroundings has to be equal and opposites, right? Negative 87.8 joules per mole Kelvin. Overall, not too bad. Now, last one is going to be heating. So since entropy has absolute values, the entropy at different temperatures can be calculated as the absolute entropy at one temperature plus the change, right? This is the absolute entropy. All of this is the change in entropy, basically. Right? All of this is the change in entropy. That's all we're looking at. Right? So we have the final entropy is going to be the initial entropy plus the change, basically, right? And this is going to be Q over T. Right? Just Q is over T as usual. All right? If it's at constant pressure, right, then Q is equal to Cp times dt, right? This is Q. Eventually, we got to like Cp delta T. That's kind of where we're going with it, right? That's where we would normally go with it if it was just T by itself. But since it's dt over T, right? The integral of 1 over T, which is basically what it is, right, is going to be Cp times the natural log of Tf over Ti, right? Because the integral of 1 over T equals the natural log of T, right? And when we go from one lower bound to a higher bound, we have to do Tf, what we call it, minus Ti. But in logarithm form, it's division, right? It's kind of division. Now, one thing you should notice is that this looks a whole lot to an equation we had at the end of last chapter or last topic, whatever you want to call it. All right, where is it? Maybe not the end, but towards the middle. Where is it? Right, it was Kirchhoff's law, right? That one was delta H at TF equals delta S, or sorry, delta H at TI plus, right, delta CP times T1, or sorry, T2 minus T1. Sorry, TF. Got to keep all of my little things together, right? It's very, very similar to something we saw last chapter. All right, very, very, very similar. Something that you would have used on the would have used on the exam, theoretically, right? Same basic idea. So the only difference is that this one is divided by t, so we get natural log. And this one for delta H, there was no divided by t, and so it kind of came out very cleanly, right? And this is very simple. If we wanted to use this, right, change in molar entropy of nitrogen gas, the temperature is lowered from 298 Kelvin to 273. Given that Cp molar of N2 is that number at 209 K. And again, for all of these, we're always going to assume that Cp is constant. Right? Assume Cp is constant. Right? We're going to assume that's constant. We're not going to make things super duper complicated by calculating changes in Cp and all this other stuff, right? We're not going to do that. So if we think about it, so we have S at new temperature 273 equal to S at 298, right? Plus Cp natural log of Tf. In this case, yeah, we'll do Tf over Ti. Right? Exactly what we just saw, right? Now, here, if we're looking for the change in molar entropy, right, between these two temperatures, notice we don't have numbers for either one of these. We don't have numbers for the absolute entropy, right? But the change in molar entropy is just going to be final minus initial, right? Our delta S is just final minus initial, right? So we rearranged a little bit. What do we get? Delta S is going to be Cp natural log of Tf over Ti. And I just moved minus the minus 2s to 298, whatever. Moved it over. That's delta S, final minus initial, right? And then that's going to be equal to what's left over is Cp natural log of Tf over Ti. Right, that makes it very easy because delta S, Cp is going to be 29.125 joules per mole Kelvin. Right. We're going to have the natural log of the initial or the final temperature, which is 273, and the initial temperature, which was 298. Easy enough. Let's do a calculation. All right, let's see. Natural log of 273 divided by 298. All right, multiply that by 29.125, which is Cp. And we get an answer of negative 2.55. Negative 2.55 joules per mole Kelvin. All right, negative 2.55 joules per mole Kelvin. All right, pretty straightforward. Luckily, pretty much everything in this entire topic is pretty straightforward, to be honest, right, which is kind of a nice break, right? But again, this is negative. We expect a negative change in entropy as we decrease the temperature, right? As we decrease the temperature, we expect a negative change in entropy. So that all works out. Right? If we have composite processes, right, since entropy is a state function, it's just going to be the sum of smaller steps, right? The sum of smaller steps. It's often easier to break down entropy into these different smaller steps and then add them all together. All right, for example, calculate the change in entropy of a system with 2 moles of gas, which has a Cp molar of 7/2 R. It's changed from 25 degrees Celsius and 1.5 atmospheres to 135 degrees Celsius and 7 atmospheres. Okay. So all over the place. That's kind of all over the place. But if we wanted to look at this, here we go. Flip, 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 flip. If we wanted to look at this. Right. We have two different changes here. We have a change in temperature, right? And we have a different change in pressure. Right, different change in pressure. Now our change in temperature is going to be fairly easy to figure out. That's literally what we just did, right? We said, stop that. Stop that. Go back. We said that delta S is equal to, right, CP natural log TF over TI. Right. CP natural log of TF over TI. Pretty easy. And we're told that delta S CP is going to be 7/2 R, right, times the natural log of, in this case, we need it in Kelvin, 135 plus 273 equals 408. 408 Kelvin on top. And on bottom, it's going to be 298. We're going to chop off the 0.15 just to make it cleaner, right? So delta S for this part is going to be pretty simple, right? In this case, R, because again, natural log is dimensionless, R is going to be 8.314 joules per mole Kelvin, right? And then the second portion, natural log of 408 divided by 298 is 0.314. Put that all together. Let's see what we get. 7 divided by 2 times 8.314 times 0.314 gets me a number of 9.14 joules per mole Kelvin. All right, 9.14 joules per mole Kelvin. All right, and that's for the temperature change. All right, that's for the temperature change. Now for the pressure change, all right, we don't have anything necessarily for pressure, right? What we did learn, right, that our delta S is in our natural log of VF over VI, right? We learned this natural log VF over VI. Now, we don't have VFs and VIs. Right? What we do have, right? We do know that we're assuming these are perfect gases, right? P equals nRT, right? We could solve for P as a version of all this stuff, and you can do that, right? But the basic idea is that, right, the pressure and volume are going to be opposites, right? So we're going to write this again. You can do all this stuff to solve for V, right? And put in, or like do V in terms of P basically, right? But if you do all that, you have N times R and the natural log of PI over PF, right? PI over PF, right? Again, because since these are directly proportional, or sorry, inversely proportional, right? When one goes up, the other one goes down, right? Then if we have an increase in here in VF over VI, then we need to have a decrease here in PI over PF. And it all works out again. You just, if you really want to solve for it, use P equals nRT, rearrange, solve for V in terms of P, you'll get there, right? You'll get there. Right. But if we do that, delta S is 2 moles. R is still going to be 8.314, right? Because we have a natural log. And then for a natural log, our pressures both in atmospheres. You know what? That's perfect. right? It doesn't really matter because if we're inside a natural log, as long as we have the same dimensions, it doesn't matter what the dimensions are, right? As long as it's atmospheres and atmospheres, doesn't really matter what the units are. Right? And if we do that, what are we going to get? Well, we're going to have the natural log 1.5 divided by 7, right, times 8.314 times 2 is going to get me negative 2.5. Oh, that's not right. Going to get me negative 25.61 joules per mole Kelvin. Right? And if we add both of these up, right, our total change in entropy of the system is going to be that 9.14 plus negative 25.61, which is going to be overall negative 16.47 joules per mole Kelvin. Okay. Overall, not so bad, right? Right now we have a much smaller number of equations, which makes it very nice, right? Makes it very nice. But that's where we'll stop. And that's the end of sections A and B. We'll pick up next video with sections C and D and E, basically.